Hey guys, and welcome back to another video on the channel. In today's video we're going to be solving some differential equations using separation of variables. So I've chosen example 9 from the VCE specialist textbook for Victoria, Queensland, Australia, and we're pretty much just going to be going through how to solve each of these. So let's just start off with A. So dy dx equals 2y plus 1. Okay, so obviously this is a separation of variables because this respective variable doesn't appear on the right hand side of the equation. So if we were to integrate it at the moment, you would have to integrate it with respect to x, and we're not going to do that because there is no x's there and we have it in terms of y. So ideally we want to separate our variables ideally, so we have pretty much all of our y's together and all our x's together. So what we can do is actually swap this guy and this guy here by timesing both sides by dx and dividing both sides by 2y plus 1. So if we do that to both sides, on the left hand side respectively, what we're going to have is a dx on a 2y plus 1 times by a dy dx. And on the right hand side respectively, we're going to have a 2y plus 1 multiplied by a dx times by a 2y plus 1. Okay. Now obviously you can see straight away those terms cancel out because that's the opposite of one another. And if you divide something by itself, it's just 1, so all we're left with on the right hand side is dx. And on this side you can see those dx's cancel out. So what we're left with is the following expression: dy is equal dy on 2y plus 1 is equal to dx. Okay, so now what we have is separated our y. So this side is purely a function of y, and this side here is purely a function of x. Even though they're differentials, we've just separated our variables. So now what you can do now is attach an integral to both sides, and we can integrate both sides. Okay, now if you integrate this side here, this is the same as rewriting it pretty much like this. So pretty much a standard integral over here. Okay, this side here, it pretty much undoes the x. So a change in x, undoing that is pretty much getting rid of that d, so all you're left with is x. We won't account for a plus c here because we'll get one over here, and pretty much you can combine them anyway. This side here you can see is going to be a natural log, but what we can see is we've got an inside function here pretty much. So you need to divide by its differentials, or we could do a u sub. So I'll show using a u sub. So a u sub is changing your variable. So let u equal 2y plus 1, du dy equals 2, therefore dy equals du on 2. So what I did there was pretty much I defined what u is, which is that, and then I need to change that dy to a du respectively. So I can now replace this expression in here. So what I have on that left hand side, if I just move this to the side now, is the integral of 1 on u du on 2 equals x. Okay, then I can take that half out the front, so I get a half the integral of 1 on u du equals x. I know this side is going to be natural log of u, so a half natural log absolute value of u plus c equals x. I know what u is, it's 2y plus 1, so it's a half natural log. Now this half is timesing by that whole thing there, but the reason why you don't need to write that there is because a half times a constant is still just another constant, so we can leave that as still as a plus c. Then we put the 2y plus 1 in there, plus c, and now what we're going to do is rearrange our function so we have y as the subject, okay? Because typically x is your independent variable, so you have y in terms of x. Moving the c to the other side, what we can do is literally go minus c on both sides, but you can literally rewrite it as another constant. So when you move the c to the other side, you don't necessarily need to change that sign, because this constant moved to the other side, even though it'll be minus c, that's just technically another constant still. So we can still write that as a plus c, but this plus c is no longer that plus c, it's the negative version of that. Okay, moving that there, timesing both sides by 2 to undo that half there, so we get natural log of 2y plus 1 is equal to 2x, and then I'm still going to write a plus c because that's still just another constant. Then I'm going to rewrite it in terms of exponential, so this side will be 2y plus 1 is equal to e to the power of 2x plus c. We can simplify this side by writing it as ec times by e to the 2x. This is just a constant, so I'm just going to write that as a. So what we have is 2y plus 1 is equal to a e to the 2x. move that 1 to the other side, so you get 2y equals to a e to the 2x minus 1. Then you can divide both sides by 2. So I'll just leave that pretty much there. And that is your solution to your differential equation for the first one anyway. Okay? Righto, so that's question A done. Let's take a look at question B very quickly. So I'm just going to actually just going to copy this and bring it down. Right, so B, dy dx is 2y, sorry. So dy dx is e 2y. So we've still got to make y's combined together. So what we're going to do is actually divide both sides by e to the 2y. But that is the same as timesing both sides as e to the minus 2y because of that negative exponent, as this is exactly the same as that. Okay? So if you do that, this side is just going to be 1, and this side here, what we're going to have is just e to the minus 2y dy on dx equals 1. Multiply both sides by x, not x, dx, sorry, so you get e to the minus 2y dy equals dx. Then you can integrate both sides. So this one here we can divide by its differential, so you get negative e to the minus 2y plus c, and this is just going to be x. Okay, move that c across, so we get negative e to the minus 2y equals x plus c. I'm just writing it as a plus c because it's now a different c to this one here. Divide both sides by negative 1, so you get e to the minus 2y equals negative x plus c still, that doesn't change. Then I'm going to write that as a log, so minus 2y is equal to natural log absolute value of negative x plus c. Then divide both sides by negative half, so you get the following expression as your solution to the differential equation. Okay, and that's it pretty much. Right, let's take a look at C together now. So I'm just going to move that down here. So dy dx is square root of 1 minus y squared. Now this one I can tell is going to be an inverse sign, mainly because of how this is built here. So if I multiply both sides by dx and divide by the square root of 1 minus y squared, I'll get this following expression. So literally just swapping these two around, you get dy divided by square root of 1 minus y squared equals dx. Now if I integrate both sides, I can see straight away this is straight up an inverse sign. Because I remember if you have pretty much the integral, what is actually the formula? I'm just going to pull it up very quickly just so you guys can see it. One moment. There it is. Perfect. So I don't know if you're going to be able to see this image. Hopefully you're able to. So this image here shows your table of integrals for inverse sine. So I know straight away, even though it has an x here, this is the exact same model as this thing here. Okay, so knowing that, I can rewrite that as inverse sine of y on 1 plus c equals x. Okay, y divided by 1 is still y, so it's just going to be sine inverse of y plus c equals x. Move the c to the other side, so you get sine inverse of y equals x plus c. Then just sine both sides, so y equals sine of x plus c, and that is your solution to that differential equation. Righto, so final one for the video is example D. Now example D is a bit more tricky because you've got to do a couple more steps involved in it. Okay, so what we're going to do is pretty much write it the same as we normally done and pretty much get y's and x's separate. Okay, so we have 1 minus y squared, and then we're going to pretty much just swap these two around again. So you get dy on 1 minus y squared equals dx. Okay, now straight away what we can see here is we pretty much don't have anything special on the bottom, but you can rewrite that as a difference of squares on the bottom. Okay, so pretty much that bottom bit is going to be pretty much a partial fractions. So to separate that as a partial fractions, we need to rewrite this here as pretty much 1 on 1 minus y squared dy equals dx. Okay, Now you can still attach an integral sign, but all I want to do is look at this algebraic expression and simplify it. So 1 over 1 minus y squared, we've got to work out what this is as a difference of squares. So a difference of squares is pretty much if you have a squared minus b squared, it is a plus b multiplied by a minus b. Okay? So what we have here technically is 1 squared minus y squared. So what we're going to have is 1 minus y multiplied by 1 plus y. Okay, so those are the two solutions. So that means that this expression here can be rewritten as the following. It can be rewritten as a number, a, on 1 minus y, plus a number, b, on 1 plus y. Okay, and we can work out what these are going to be determined using pretty much the denominators of our fractions. So if I rewrote this side here, so if I wrote this as its difference of squares, so I got rid of that, what I've got is this following expression, 1 minus y times by 1 plus y. Okay. Now, if I times everything by 1 plus y times by 1 minus y, what's going to happen is this side here, when you apply that to there, you're just going to get 1 on the left hand side. If I apply it here, what's going to cancel out is the 1 minus y squared. So what I'll have is a times by y plus 1. And then the b will be the opposite. It will be b times by 1 minus y. Okay. So what I can do is I can work out the a and b by substituting values of y. So for example, if I put y equals negative 1, that makes this term 0, and that works out what b can be. So if I did that very quickly, I get y, 1 equals a times by 1, what was it? Negative 1 plus 1 plus b 1 minus negative 1. Okay, this side here is 0 because a times by 0 is 0. This here is going to be 2b, so straight away I've got 1 equals 2b, so therefore b must be a half. Okay, then you can do the exact same thing with the other term. So set y equal to 1, and we get this following expression instead. So what we have here is pretty much 1 equals 2a, and then this term here is now 0 because b times by 0 is 0. So that means a also is a half. Okay, so if you plug that information into the following, so a and b are both a half. Let's get rid of that for now. 1 on 1 minus y squared is the same as a half, so 1 on 2. 1 minus y plus 1 on 2. So all I did was substitute b and a for their number a half. So that is why you've got that 1 on 2 there. Okay. Now that is a lot easier to integrate than this following expression here. So what we can do is actually substitute that in, so we get the integral of 1 on, well actually we can factor out that half in total pretty much because they're the same number, so you can go a half, factor out of 1 on 1 minus y, plus 1 on 1 plus y, dy equals, what is it? The integral of x. Integral of dx, okay? So these sides here, we know they're all going to be natural logs. So a half, oh that is a terrible looking one, a half. If I integrate this expression, I need to divide by its inner differential. So 1 minus y, if you differentiate that, you get negative 1. So this first expression here will be negative 1, natural log of the absolute value of 1 minus y, plus a constant, but I'm going to leave that out for now because I've still got this term. Divide by its differential here is still going to be 1, so it's just going to be plus natural log of 1 plus y plus c, brackets, equals x. Okay? What I'm going to do is leave out that half for now, but I'm going to combine these two using log laws. So if you have natural log of something, it doesn't have to be natural log, it just has to be any base and they have to be the same. If you have an expression like this, where you have log base same as this, minus log base of this, it can be rewritten as a single log where the inner bits are dividing by each other. So a So natural log of a minus natural log of b is the same as natural log of a divided by b. So in this expression here, we can have a half, square brackets, natural log of 1 plus y divided by 1 minus y, brackets, plus c equals x. Okay? Now we're going to make y the subject. So, straight away, I'm going to times everything by 2 to get rid of that half. So I get natural log of 1 plus y on 1 minus y plus c is equal to 2x. I'm going to move that c to the other side, so I have natural log of 1 plus y on 1 minus y equals 2x plus c. Doesn't matter about that sign because it's still just another constant. Then I'm going to raise both sides to the e to cancel out that logarithm. So I get 1 plus y on 1 minus y equals e to the 2x plus c. We can do that little trick that we did up here in that other differential equation where we rewrote this bit here pretty much. So instead of, what is it, 2x plus c, it can be rewritten as a e to the 2x. So that constant has gone there now, and I'm just going to pretty much copy that next line of working. Copy. Oh, we forgot the y. That's alright, we can just draw it in. Now, you're probably thinking, how do I make y as a subject? Well, we've got to do a bit of algebra. For starters, we're going to move this guy up here so we can distribute that term, and then we can factor out a y. So if we do that, we go 1 minus y is equal to a e to the 2x times by 1 minus y. So you get 1 minus y. Oh, not 1. Oh, that top bit's meant to be a plus, my bad. Plus equals a e to the 2x, because I'm distributing this to each of the terms, minus a y e. Actually, I can put the y on the end. Doesn't matter anyway. E to 2x y. Then I can put all my y's together, so I'm going to plus this term to both sides so I can get the y's on the left hand side for now, and then while I'm at it, I'll just minus 1 from both sides to get rid of that guy there. So if I do that all correctly, I get that y is meant to be not in the power, so it's just going to be a e to the 2x y plus y equals a e to the 2x minus 1. You can see on this side here they both have a factor of y, so you can factor that out, so you get y factor of a e to the 2x plus 1 equals a e to the 2x minus 1. Divide both sides by this expression here, so you get y equals a e to the 2x minus 1 divided by a e to the 2x plus 1. And that is the solution to your differential equation. That was a mouthful, but we got it done. If you have any questions about these differential equations I've solved here, leave something in the comments and I'll try my best to answer them. But until then, I'll see you next time.